let's have a look at the word. Okay. Poly just means many. Now, this norm from nomos is a less common word. It's the same root under, say, like taxonomy or anything like economy, all those nommy words, right? Nommy words. Yeah, notable exception is nom. But anyway, does anyone know what it means?
Name?
Yeah, name is one of the words we get from there. In this context, what it really means is terms, right? Or elements or phrases, okay? So it just means many terms. Now, what does that relate to? Well, back in year 8, even though you might not have actually had it told you, this is what it was, but under like quadratics and that kind of thing, we talk about factorizing. If you looked at the program, you would have seen this. Am I spelling this right? Sorry, try. Let's start again. Try.
You've got to hear the first time.
Yeah. We talk about factorizing trinomial expressions, by which we mean stuff like x squared plus 5x plus 6. You can see there are 3 terms, right? And in year 12, actually, I'm going to cover it in a few weeks in my year 12 class. We've got this whole topic called binomial expansions. Morning. Which is all to do with taking things like, say, I don't know, like x minus 3, and then raising them to crazy kinds of powers, like say 40 or 50 or 400, okay? So that thing in there, that's the binomial. There are 2 terms, and then you expand it out. And there's a whole theorem to do with this, okay? It has to do with Pascal's triangle. Anyway, so therefore, that's all polynomials. That's all the term means, okay? But that kind of disguises why we study polynomials and why they're really cool. Polynomials, and particularly the solutions to polynomial equations, are actually a really important family of numbers that you've probably never heard of, but you actually work with all the time. This set of numbers is called, I'm going to give you, you know how we talked about integers and that kind of thing, like when we were doing general solution, and we said, you know, a number like n belongs to the set of integers, right? So there was that funky looking z, which is just our way of saying whole numbers, okay? So here, this set of numbers has its own set notation symbol. It's a funky looking A. What it stands for is, does anyone know? No, it'll take too long. Sorry. Just because the name is too long. It's a set of algebraic numbers. Now, has anyone ever heard that phrase before? Yeah, probably. Yeah, maybe. I wouldn't be surprised if you've never heard of it before, because it's kind of like an umbrella term. I'll explain it in a second. All right, we'll come back to it. Now, let's just really quickly rattle off some examples of polynomials, and then we'll try and generalize out and say what's the general polynomial. Okay. So examples. X minus 1. That's a polynomial. Okay. X plus 2. I actually had some specifics in there because I wanted to put down. Actually, let's make this 2x plus 3. X squared minus 5. X squared plus 5. Okay. So these are all polynomials, right? What are some things to note? You've got these x terms here, and you've got different powers sometimes coming up. You've also got these numbers out the front here. Well, actually, all the numbers, really. They're all integers. That's important, okay? If I chuck like a square root or something like that into here, okay, it would cease to be a polynomial. All of these powers as well, they all must be positive. When you take negative powers in, it ceases to be a polynomial. Okay? Now, why did I pick out these ones? Well, you remember I said that the solutions to polynomial equations are this set of numbers, okay? So here are some polynomial expressions. Let's turn them into polynomial equations, okay? So I'll just slap an equal sign on there. Now, I picked these particular equations for a reason, because what are the solutions to these specific equations? Well, the solution to this one is 1, okay? And that's an integer, that's a whole number, right? The solution to this one is minus 1.5, minus 3 on 2, okay? Which is, number one, it's negative, right? So it's not just positive numbers that you can get out of this, but also it's not an integer at all. It's rational, right? It's a ratio, it's a fraction, yeah? Okay, how about this one? What are the solutions of this? Okay, so you're going to get not just one, but two solutions to this, and also they're surd solutions, right? They're irrational, okay? So it's not just these kinds of, happy sort of numbers. You get weird geometric numbers in here. What about a solution to this one? Solutions. Okay, now there are no real solutions because these solutions up here, these are the real numbers, okay? But this is not a real number. It's another kind of number that you know about, namely? It's an imaginary solution, well actually two imaginary solutions, which is a terrible name because there's nothing like, imaginary about them. It's just that you can't measure these kinds of numbers, okay? But that's another issue. So you're bringing in I, which is the square root of -1, okay? Because there are no lengths or magnitudes that can go into this. It's a two-dimensional number. All right, now, let's have a look at this one. Now, without actually solving it, you already see there's a pattern here in that each one of these equations gives you a different kind of family of numbers. What's the difference here? What's the difference between this one and this one? Now, the actual solution to this one is plus or minus the square root of -5, okay? Which we can write as plus or minus square root of 5i, okay? So the important thing to note is that all of this has to do with this. It's all attached to the I. It's all imaginary, okay? But if you go ahead and solve this, you can use the formula or complete the square or whatever you like. What you'll get is not just an imaginary part, but there will also be a real part, right? So when you have both of those together, we call that a complex number, right? A complex number is the combination of those two. Okay, now here's the kicker, right? All of these numbers, right, even though they are so diverse and very, very, where do these kinds of numbers come from? This comes from counting, this comes from sharing, this comes from geometry and like Pythagoras, that kind of thing. This comes from, it's hard to explain, electricity, physics. This comes from more electricity and more physics, okay?
When you say complex, is it the two solutions together are complex?
No, like as in the solution here will be, I don't actually know what the numbers are, but it's like 3 plus or minus, square root of 3i or something like that. So there's two parts, that's what I mean by complex. Yeah.
You know when how you said for the polynomials, the coefficient has to be an integer?
Yep.
Isn't that just a real number?
Huh.
Isn't just the power an integer?
Not the ones that we're interested in. Oh, sorry, I see what you mean, yeah. Didn't I say that? I thought the powers are, all the numbers here that I've listed are integers. When we're talking about what needs to be an integer, it's the power. Yeah, because as you can see, if I took, for instance, let's go root 3x plus 1 equals 0. What will the solution of that be? What will the solution of that be? Well, it will be root 3x is equal to -1, so x is -1 on root 3. So it still belongs in this set. You're still getting an algebraic number at the end, which is why, okay, it's a polynomial. Okay, so this is this whole set is the set of algebraic numbers. Now here's my question to you. What kinds of numbers don't fit into this set? Because that's a lot of kinds of numbers.
Infinity.
Infinity doesn't fit in there because infinity is not a number. It's a concept. A very useful concept, but still not one that you can actually sub into something. Okay. Yeah. X is also not a number, it's a variable. Okay. I'm looking for constants here. The family of numbers that doesn't belong here, that's the complement, if you like. You remember complements? So if you got Z, right, if you stick a wavy line over the top, that means not Z, so not a whole number. Okay. The complement to the algebraic number set is a set that you've heard of before. It's a more famous set. They're called the Transcendental Numbers. Now, I am somewhat disappointed if you've never heard the name, at least, because the numbers that fit into this set are very famous. You've been working with them since year 7, at least. Numbers like, say, pi, right? Numbers like, say, e, or the log of any algebraic number, actually. Okay, so, except for e. These numbers here, right? Where do they come from? Well, this number comes from mainly circles, but it comes up in weird other random places. This comes from natural growth, which we'll look at a bit more when we do exponential growth and decay. This is the same thing, right? These are just two sides of the same coin. But importantly, right, these numbers, they don't come from the way that we build numbers. This is the way humans build numbers. We add, we subtract, we multiply, we multiply again and again. That's what exponentiation is about, okay? But these numbers come from somewhere else, okay? This 3.1415, this ratio, this 2.7182, blah, 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 blah. We can't, there's no polynomial equation you can build to which these are the solutions, okay? So because they are beyond the ways that we build numbers, we say they transcend the way numbers are built, okay? Hence transcendental numbers, okay? Now, by the way, just as a weird, wonderful, cool thing which has nothing to do with this topic, okay? You take the two most famous transcendental numbers, right? And if you put them together in an unusual way, take e, raise it to the power pi, and just stick another imaginary number in there, the square root of -1, okay? Transcendental, another transcendental. This guy is just a weird oddball who doesn't fit with other people. Does anyone know what this is equal to?
1, 2,
Almost.
3, 4. 0.
Equal to -1. Now, just think about that for a second, okay? Weird numbers,
Yes.
antisocial number, right? And you come out being, it's not quite, I mean, positive counting numbers. Yeah, good luck with your calculator.
There must be an I button somewhere.
It's about as weird as you can get, and you throw them together, and out comes this. I find that really unsettling, okay? Now, I could explain the geometry of this. If you're curious, you can go look up Euler's identity. That's the name of this equation. But it's weird, isn't it? Anyway, that's an aside. These are the kinds of numbers and expressions that we're going to deal with. Yeah.
If you have x minus